It's my pleasure to introduce to you Alexis King, who's the author of Hackett, which is a mix of Haskell and Racket. In the Haskell world, she's also pretty known for her work around delimited continuations, which she's going to talk to us about today. I think the previous Hack talk by Alexis was one of the best received talks we've had over the years, so no pressure, Alexis. Yeah, pretty excited. Please take it away.
All right, thank you. So, as the title of the talk sort of suggests, I'm going to spend some time talking about delimited continuations. And I imagine most people in this room either have no idea what those are or have a very vague idea what those are. We'll get to that. But I just want to start with a little bit of history, because delimited continuations are not, by any stretch of the imagination, a new idea. In fact, they predate me by about 10 years. And there initially was just a huge amount of publications, largely in Scheme, also in a few other communities, but just a bunch of different presentations of sort of the same idea. Many of them are essentially equivalent or almost equivalent, interchangeable, but, and this just kind of, I think, made things even more confusing, because if you go and you look, what are delimited continuations, you'll find all these different operations, and it's not clear which ones are canonical, and they just didn't really see very much mainstream adoption. But what's interesting is that in the past 10 years or so, 5-10 years, there has been renewed interest, not just within the Haskell community, but also within like the OCaml community, with OCaml 5.0, which was very recently released. They now have a form of delimited continuations. And there's even some discussion of adding delimited continuation support to Java, which is very mainstream. So there's been some interest, clearly, but obviously this is Hacks, so we're going to focus on Haskell. So just a little bit, just to give you a picture of the timeline here. So I initially proposed adding delimited continuations to the GHC runtime about 3 years ago. That proposal was accepted, and I sort of had a half-done implementation, but nobody was paying me to do this, so it was just something I was doing in my free time, so I didn't really work on it for quite a while. But last year, I started working at Tweag, and it's been really wonderful. I've been able to get paid to work on GHC, and I mostly haven't been doing this, but I did have the opportunity to finish it, and because of that, as of GHC 9.6, just a few months ago, we now have delimited continuations in GHC, which is very exciting. So obviously, that's great, but as I said, nobody has any idea what they are, which is sort of a problem if people want to actually start writing libraries that use them. So obviously, the purpose of this talk is going to be fixing that. And what I'd like to do is sort of present a slightly new presentation, not a wildly new presentation, I'm not going to claim that anything in here is novel, but of this old idea, and hopefully a way that I think is more illuminating than I think the sort of standard presentations you get. So just to start out, I want to discuss some terminology. So a lot of the time people will say continuations, and they really mean this as an abbreviation for, actually in some cases a few different things, but often for delimited continuations. And in fact, they're usually not even using it as an abbreviation for delimited continuations, but first-class delimited continuations. And in this talk, we're going to be talking about native first-class delimited continuations. So we have all these adjectives here, and I think for, again, a lot of people who frankly don't even know what continuations are, don't even know what the noun is here. These just sort of sound like superlatives, like I'm saying, amazing, premium continuations. But in fact, each and every one of those adjectives is very important, and we're going to discuss them sort of one at a time. But we are going to start by just talking about continuations. And I guess one of the things that I want to say is that it will turn out, as you'll see, that a lot of these concepts are, even though continuations have this reputation for this, extremely expressive, extremely fancy, extremely mystical thing, they're actually really simple. A lot of these concepts are really simple. We'll get to the more complicated bits, but if you're sitting there saying, like, I just must not understand it because it seems so simple. In fact, it is that simple, so don't worry about it. All right, so I do want to start by clearing up a couple of sort of common misconceptions. So the first one is, believe it or not, continuations are not a language feature. If we're just talking about continuation, none of those adjectives, really they're a concept. Of course, this is very vague, so I think a good analogy to use here is the term scope or value. We would not say that values are a programming language feature. We might say that a particular type of value is a programming language feature, but value is just a term that we use to describe a thing in a programming language, which is, a fully evaluated expression. And additionally, this concept applies to most programming languages. It's not a particularly exotic thing that only exists in some fancy languages. It really just kind of shows up everywhere, and in particular, it shows up when we're talking about evaluation. So we're going to spend a lot of time in this talk just looking at the evaluation of expressions and talking about how continuations come into play there. So I want to make this more concrete, and so I want to take a look at a simple example. Now, I want to preface this by saying that I am going to be using Haskell syntax, but continuations have, they're sort of fundamentally tied up in evaluation and evaluation order. And Haskell's lazy, so that makes this complicated. So for basically all the examples, we're going to assume a strict left-to-right evaluation order. So if we consider this just simple arithmetic expression, then we would start by reducing 1 plus 2. That obviously reduces to 3. Then we would reduce 3 plus 4, 7. 3 times 7, 21. Obviously, I don't think any of this is going to be particularly controversial. But the particular thing that I want to call attention to here is that at each step in this sort of sequence of reductions, we selected some sub-expression that was sort of the next thing to reduce, and then pulled it out, evaluated it, and substituted it back in. And that process, believe it or not, is going to be very, very important to talking about continuation. So I want to make this even more excruciatingly explicit and go back to the beginning and say, okay, so this is the sub-expression we're going to evaluate. And then we have this bit on the right here that is everything else. So we're literally splitting this apart, and when we split it apart, I've left this black circle here to represent, you can pronounce it as whole. So that's the whole that we've removed 1 plus 2 from. We're going to reduce 1 plus 2 to 3, and then we plug the reduced result back in place of that whole. And because we're going to be talking about this reduction process a lot, it's going to be very useful to have names for these two pieces here, the bits highlighted in red and the bits highlighted in green. So the bit highlighted in red, because that is the expression that we're reducing, it's the reducible expression, we're going to call that the redex, which is short for reducible expression. And that's not a term that I just made up, that's a standard term. But what do we call this bit in green on the right? Well, we could call it the context, that's a little bit vague. We could maybe call it the evaluation context, which is a little more precise, and people do call it that sometimes. But another way to think about it is that the bit in green describes how to continue evaluation of this expression after we have simplified the redex. And because the part in green describes how to continue evaluation, we call it the continuation. And yes, that's really it. That's what the continuation is. It's not a particularly fancy concept, just describes kind of everything that we have left to do. So I want to then sort of focus on the fact that, okay, continuation is a property that changes over the course of the program. So if we continue execution, now we can divide it up this way. Again, we have redex continuation. This time the continuation's on the left. It has changed, and we do the same process, substitute it back in. Now, if we continue at this point, it may seem like, well, all we have now is a redex, but of course we can also think about that as just we have the empty continuation, we reduce it, substitute it back into that hole, and then we're done. Evaluation is finished. So what actually is the continuation, just to sort of recap and provide a few different perspectives. So obviously it's the context in which the redex is being reduced, and it is concretely an expression with some hole somewhere in it. It's also sort of, one way to think about it is that it's the place that after we're done doing, we're done taking one step of simplification, we return that value to that hole in the continuation. But I think the one that is most interesting and perhaps most useful for what we're going to be talking about is that the continuation is the remainder of the program. It's everything that we have left to do. And one way to make this even more obvious is by rearranging the program so that we've written it and sort of factored out those sub-expressions into statements. And now we just reduce the program sort of top down, one statement at a time. So we can do the same thing again. Now the redex is just, or the hole is just on the right-hand side of that let. Simplify, plug it back in. But now, of course, we just have this statement here which is just, fully reduced. X is just 3, so we can substitute 3 in for X, and that statement disappears. And so now the continuation has shrunk to be just these two statements. And so you can sort of see that as we step through this program, the continuation gets smaller and smaller, and it just corresponds to everything we have left to do. Now, of course, if we have some recursive function or a loop, then the continuation might not necessarily get, infinitely smaller. It may, in fact, get bigger sometimes. But if the program terminates, then eventually it will reduce to a value, and the continuation will become empty. Makes sense? All right, so why care about this concept? Like, this is all well and good, but it just doesn't seem particularly interesting, because if you think about it, this process that we've been describing is extraordinarily mechanical, right? We just split up the term, we reduce the radix, we substitute it back into the continuation, and we repeat. And that's all we've been talking about. And so because of that, it might seem like the continuation is sort of the background, and the radix is the foreground. And obviously we care about the radix because that's what we're actually doing, but we don't really have much reason to think about the continuation itself, because it's just something we're so used to reasoning about in this way. Of course, there's more to do, but that's not what we're focusing on right now. So a sort of boring and maybe cop-out answer to this question is, well, compiler writers care quite a bit about the continuation, because you have to somehow keep track when the program is running of what there is left to do. But obviously, even among Haskellers, not all programmers are compiler writers. So I think it is obviously true that most programmers, most of the time, when we're just talking about these simple expressions, the continuation is just not that interesting. But there are situations where the continuation itself is actually interesting to think about. And that's when we talk about operations that don't, in fact, follow those rules. And in fact, I think sometimes it's possible to think about a number of operations in programming languages that are quite common as being operations whose explicit purpose is to manipulate the continuation. So let's give an example of that. So the simplest one is just exit. So exit, of course, is a very boring function because it just terminates the program. And if we sort of apply the same reasoning process that we've been applying and split this apart, then obviously the continuation is completely irrelevant because the program just exits. So in a sense, exit is an operation that just discards the continuation. So this clearly does not follow the rules we've been describing because exit doesn't reduce to a value. But, this is still not terribly interesting because, again, we don't care about the structure of the continuation. All we're doing is throwing it away. So we need something a little bit more complicated to really motivate thinking about the continuation explicitly. And a good example of such an operator, actually two operators, are throw and catch. So throw and catch, obviously very, very common in programming languages. One challenge, of course, is that every programming language sort of has a slightly different syntax for talking about throw and catch. And because in Haskell, there's laziness, we can sort of get away with it just being a function, but here the syntax I'm going to use, okay, throw is just a function, very easy, it just raises its argument as an exception. But I'm going to use this syntax here, where I've just kind of put braces around the body to indicate that it's sort of, suspended somehow, just to be explicit about evaluation order here. And since we're just working in this sort of hypothetical, strict pseudo-Haskell, then it's just going to be, catches syntax. You can think of it that way. So this just evaluates the body, and if the body raises an exception, then it applies handler to it, much like catch actually works in Haskell. Not too complicated. So let's look at an example of that. So here we have just, because this is a strict pseudo-Haskell, we don't have to write everything in monadic style, which I think actually makes these examples a little bit easier to read. And we can just do 1 plus catch, there's the body, and the body just immediately throws. So this is not a very exciting program because then that throw just gets caught immediately and is going to apply the handler to the thrown value. So of course, this then just reduces to 3 times 5, and then of course the rest of the reduction is entirely mechanical. Okay, everyone on the same page? Good. All right, so what if we apply this reasoning we've been applying to this program? So throw here is the radix, and everything else is the continuation. We can split this apart, and now the challenge that we have is that it's not immediately obvious how we combine these two things to get the next step in the reduction. And so it might seem initially like this is not a useful way to look at things, because if we sort of look at this more closely, we have some of the continuation that is preserved, and then we have some of the continuation that's not. This bit is thrown away, but obviously not all of it's thrown away. So it seems like we're dividing along some other axis than the one that we've been looking at so far, and that's sort of true. But one way to sort of provide a more helpful perspective here is that we can take a look at the continuation, and we can note that catch sort of slices the continuation into two pieces. There's this inner portion of the continuation, and then there's the outer portion of the continuation. And so we can think of the continuation as sort of a nested, a set of nested continuations inside of each other, like Russian nesting dolls, where a throw will discard the inner portion and leave the outer portion alone. And so another way to think about this is that catch is an operation, and its main purpose is to delimit the portion of the continuation that is discarded. And because of that, we can sort of think of that inner red continuation as a delimited continuation, or delimited subcontinuation. And so this is what delimited continuations are. Again, not very complicated. In fact, I think a lot of these things, when you really just spell them out like this, they're so simple they almost seem kind of boring. But we'll get to the confusing bits. Don't worry. So before we do that, though, I've just kind of been working through all these examples in sort of a vague, hand-wavy way, and we haven't been very precise, and it's hard to compare all these different operations sort of side by side. So this is the part of the talk where I get to introduce some notation. And I know that every time you're watching a talk and somebody starts putting math on the screen, then everybody's eyes glaze over and they say, well, I'll just tune out until this bit of the talk is over. And I will confess, I've often been in that position. But I'm going to be very, very careful, and I'm going to introduce exactly two pieces of notation and nothing more, and they're both very simple, and they're going to be very important for the remainder of the talk. So do try to follow along. So the first one is just, looks like this, A arrow B, and you can read this as A reduces to B. And we're going to use this to be a little bit more precise about how evaluation works. So we've been talking about evaluation as this sort of process of we reduce sub-expressions, but now it's going to be useful to be very precise about what reductions we're allowed to do. So here's a simple example reduction rule, which says just not false reduces to true, and of course not true reduces to false. Again, not very controversial. But let's look at something a little bit more complicated. So here, if true, then E1, else E2 reduces to E1. So we're going to take the then branch. And similarly, we have another rule for taking the else branch. Makes sense? Okay, so this is all well and good, and this allows us to kind of describe how reduction actually works, what reductions we're allowed to do, but if we're given some expression like this, if not false, then 1, else 2, then we have a problem, because none of these rules actually match that expression. It doesn't match the ones on the top, because there's this extra bit here, and it doesn't match the if-then-else expressions, because the condition is not just the literal true or false. Now, obviously, given that we've been kind of doing this throughout the whole talk, you can say, well, okay, we can take the red x, split it apart from the continuation, and then, once we've done this, then that not false reduces to true rule applies. And then, of course, we can reduce that, substitute back in, and now the other rule applies. But we can't just say, well, okay, we can just do this, we can apply rules anywhere in sort of the sub-expression, because if we want to then compare this to operations that don't follow that rule, then we're going to obviously want to be very explicit about where we're allowed to do the reduction. So that brings us to our second piece of notation, which is that we're going to replace this reduction rule with a rule that looks like this, where we've surrounded both sides with this sort of E brackets. So what does this mean? Well, so E here stands for some continuation. You might ask, well, why E and not C? I think it normally stands for evaluation context, but they're the same thing. And E brackets X means the expression formed by plugging the hole in that continuation with whatever X is. So to give a concrete example here, if we have this continuation for E, and then we have this for X, then E brackets X is if not false, then 1, else 2. And so now that rule does apply to this expression, because we can decompose it into that continuation and that bit in the brackets, do the reduction, and the continuation remains. So again, just a sort of way of concisely writing down the reasoning we've been doing this entire time. So why bother with all of this? Well, because now we can write down reduction rules for these interesting operations. So exit, for example, we can just say, well, exit just throws the continuation away. So it only appears on the left-hand side of the arrow, but it does not appear on the right-hand side of the arrow. Very simple. Now, if we look at the rule for catch, it looks a little bit more intimidating, but it's still really not that bad. So let's just walk through it. So we have this outer E sub 1. So now there's two continuations here, the inner bit and the outer bit, as we were sort of alluding to before. The outer bit remains, as you can see by it's just preserved on the left and right side of the arrow, but the inner bit here only appears on the left, and that's because it gets thrown away. And then, of course, we continue execution by just plugging the hole in E1 with F applied to V. Make sense? Yes?
The first one there, exit really, so it can be that the exit never really happens if I have like if false and open. So how does that work?
Okay, so the question is essentially, if exit appears under some if then else, and the branch is never taken, then it won't actually occur. So if you could just plug it into any hole, if you decompose the expression however you want, then this would imply that if it appeared anywhere, then it would just exit. So in fact, it is true, that's a very good question, which is that the shape of continuations, if we were to be more formal, is constrained. So for example, you are allowed to build a continuation where you put the hole in the condition of the if, but you can't build a continuation by putting it in the then or the else branches, and you have to reduce the condition and then use the reduction rule to pick one of the two branches and then continue. Another example of this is like if you have a expression that's like x plus y, then you can form a continuation by putting the hole on the left-hand side of the plus, but you can only put the hole on the right-hand side of the plus if the left-hand side has been reduced to a value. So that's not in the talk because that would just be more complicated, but it's a good question. All right, so it turns out that lots of operations can be described using this notation, and this is actually genuinely quite useful. And I'm not just going to sit here and list a bunch of rules because I don't think that would be very interesting, but you can describe all sorts of things this way, from non-deterministic choice, sort of prologue style backtracking, coroutines, all of those can be described very concisely using this notation. And so it's going to be very useful as we take a look at some more powerful control operators in just a bit. All right, so we've now talked about what continuations are, and we've talked about, question?
So in previous slides.
Yes.
So it seems, you initially said that there aren't really, this isn't particular to any language, so we can have continuations in any language. These are rules of the operational semantics of the language, right?
Yes.
So what gives, right?
Okay, so the question is essentially, given that I said that these apply to any language, why am I now giving these like language-specific reduction rules? Well, I mean, it is true that I think these rules, in some form, with slight modifications, do apply to lots and lots of programming languages. In that, I mean, lots of programming languages have throw and catch, and they might not use quite this syntax, but they essentially work in the same way. But, as I said before, well, continuation is a term that applies to essentially every programming language. In the same way that like value is a term that applies to every programming language. Different languages have different types of values. Some languages have, first-class functions, some languages don't. And so this is a specific rule that uses continuations to describe a specific element of a particular language. But other languages might not have throw and catch, but you could still use continuation to talk about reduction of expressions in those languages. A situation where maybe you wouldn't have a well-defined notion of a continuation, and there are some languages like that. If you have a language that doesn't have, that's just like a data language, right? If JSON doesn't have a notion of a continuation because there's no notion of evaluation, and in a language like Haskell that's lazy, then it's a little more complex. You could have some notion of it, but normally, we don't think about it that way.
So the follow-up is, does Haskell have this particular operational semantics? So can we emulate this continuation thing through like other properties of Haskell?
Well, so we can always embed a strict language into Haskell monadically, right? And I mean, that's like what we do with I/O. And that gives us a well-defined continuation in that if you have like M bind K, then K is the continuation of M. But if we just have some, pure reduction, then there are still continuations, but they aren't well-defined to the programmer. So GHC picks some evaluation order. And of course, they're more complicated because it's not just like, it's not as straightforward and that things can bounce around and it's more complicated. The notion still makes sense, but it's less useful to programmers. It's more useful to people working on GHC. Make sense? All right, great. So we talked about these two things, and again, I feel like these two things are not that complicated. There's some new ideas here, but they're really not particularly exciting. So now it's time to get fancy and talk about first-class delimited continuations. And I think this is, again, what most people think of when they talk about, continuations are these fancy, mystical, complicated things. Still not wildly crazy, but as we'll see, they can be a little bit more brain-bending. So first we have to answer the question of what actually makes something first-class. What does it mean to have first-class continuations? Well, We have lots of languages these days with first-class functions, which just means that a first-class function is just a function that is an ordinary value in your programming language. You can pass it to another function, you can store it in a data structure. It's just functions themselves are values. And so if we have first-class continuations, then that means that continuations are values in our programming language. But what does that actually mean? What we've been talking about so far are these continuations, which are sort of the syntactic aspect of evaluation, and it's not immediately obvious how we could take a continuation and represent it as a value. Of course, as it turns out, if we take a look at these just 3 random continuations, as you can see, they're just an expression with a hole again, and there's a fairly easy way to turn an expression with a hole into an expression, or in fact, into a value. Indeed. We can just replace each one of those holes with a variable, and then introduce a lambda to quantify over that variable, and now we just have a function of 1 argument. So really, continuations can be thought of as just functions of 1 argument, and a function of 1 argument that we've produced from a continuation is essentially what a first-class continuation is. Of course, this doesn't really answer the question of how do we obtain these things in the first place. So we need some operation in our language that allows us to basically, given a continuation during the evaluation of our program, reify it as one of these functions. And so the answer to this question, continuation reified as function. So traditionally, the operation that does this is termed callcc. This is a very old operation, and to be honest, I actually don't think it's a particularly useful one, but I feel like I have to mention it because it is something that shows up all the time, and it's short for call with current continuation, and it has this reduction rule. So again, it looks a little bit scary, but it's really not that bad. Here we have callcc is a function that accepts another function as an argument, and it applies that function to the current continuation e here, reified as a single argument function. So then it sort of makes sense why it's called call with current continuation, because we just take the current continuation and pass it as an argument to this function. Now, it's worth noting that the continuation still remains in place on the right-hand side of this arrow. So we sort of duplicated it once we've reified it, and then once it also shows up still, as the continuation around the expression being reduced. And this is a little bit of a problem, because it means that every single time we apply this, we're just going to be duplicating, we're going to be growing the continuation. And so in practice, callcc doesn't work in this nice functional way that I'm describing. It actually sort of, when you apply that function, it's a special function that aborts the current continuation, throws it away, and then replaces it with the captured one. So it's kind of like goto in that way. It's sort of imperative, and that's more complicated to write down, so this is not like quite an accurate rule. But again, I think that callcc is sort of a confusing operation, and just for historical reasons, people often get introduced to it and they end up being confused. Another thing that is confusing about it is that we've been looking at these really nice, pretty little continuations, but of course in a real program it doesn't work like that. There's all this other stuff that happens at the end of your program. And if we just were to capture the entire continuation, then we'd also be capturing all this other stuff, which of course we don't really want to do. So how does this actually work? Well, normally you don't actually end up capturing all of that gunk. In fact, like if you're at a REPL, for example, and you are executing some expression, you capture the current continuation, then really that continuation should also include all of the code in GHCI that is implementing that. And so if you run that, then it should replace the current continuation, and when it's done, there's no REPL anymore, and that would be bad. So normally what happens in these old implementations, like scheme implementations that provided callcc, is they would actually only capture the continuation up to the REPL prompt. And if you're familiar with these sort of traditional operations for delimited first-class continuations, that's where the name of this prompt operation comes from, which is actually very confusing from a modern perspective, but it's a funny historical detail. So these are operations that allow us to capture just a portion of the continuation, and so they're going to be a little bit more useful than callcc. So this is the reduction rule, which again now looks even scarier than the ones we've looked at so far, but still not so bad, because these are actually kind of similar to throw and catch in a way. So like with throw and catch, we have some outer bit of the continuation that just remains unchanged, and then we have an inner bit of the continuation that's sort of delimited by this prompt operator. But unlike with throw and catch, we don't just throw away E2, we preserve it reified as a function on the right-hand side, and we apply f to it, which is the argument to this control operation. So what does this actually look like in practice? Well, let's take a look at an example. So here we have some expression that uses prompted control. The outer bit of the continuation is this 1+ bit, the inner bit is this 2× bit, and this is the sort of handler function that receives the continuation. So we can split this expression into those 3 pieces, and we're sort of turning the second 2 inside out in a way where we're taking that red bit, that 2× whole continuation, reifying as a function, and pushing it inside of that expression in blue. And now, of course, this is just a totally ordinary function. So we now just have k applied to 3 plus k applied to 5. We bring back the outer continuation that remains unchanged, and now we just have an ordinary Haskell expression, well, pseudo-Haskell expression, that we can reduce as normal. So if we then step through this, then we just apply, we double 3 and double 5, and then we reduce those to 6 and 10, and everything reduces as normal. So all that happens, all of the magic, is just in that process of we replace the prompt with that function applied to that reified continuation. So this isn't, when you describe it, it doesn't sound that complicated, but the truth is that this is still really confusing. And I mean, even to me, reasoning about programs this way is not immediately obvious unless I really step back and think about it. And it's sort of surprising because, again, if we look at the rules for throw and catch and prompt and control side by side, they look almost identical. So why is it that prompt and control are so much more confusing? And for a while, this was very surprising to me. But I think I actually eventually figured out why it is. And there's a difference between these 2 rules, an important difference, and it's not just the capturing the continuation bit. So both of these operations have these sort of inner operators that, again, trigger the discarding of some bit of the continuation, and this function here is used to resume execution after they take place. But that function comes from a different place for each of these 2 pairs of operators. For throw and catch, the function is an argument to catch, which is at the position of the program where sort of control resumes. But in the case of control and prompt, the function is an argument to control, which is like it being an argument to throw. It's like if you pass the exception handler to throw, and then that resumed from the point of the catch, which is very strange because... Yes, it's an inversion of control, and it's very weird because the function is, syntactically very distant, or could be very distant. Obviously, in these simple examples, everything is nicely close together. But in real programs, throw and catch can be very far away, and so you end up with the function being very far away from sort of the point where it actually gets run. And so this is very difficult to wrap one's head around, and it's a little bit frustrating because the truth is there's no fundamental reason that it has to work like that. So we could imagine a sort of hypothetical alternative pair of operations, which I've just named Delimited and yield. These are just names I pulled out of my butt. Also, I'm actually missing some parentheses around the lambda there, but you can just imagine we have block arguments turned on. So this works very similarly to throw and catch in that yield. Now just you pass it a value, and that value gets thrown up like an exception gets thrown up. And then we apply this function, which is an argument to delimit, like an argument to catch, to both the value that we threw and the continuation that we captured. And what that continuation that we captured does allows us to resume execution from the point of the yield. And so in a sense, these operations give us resumable exceptions. So if you've ever seen a language like Common Lisp supports resuming from the point of a throw and exception, delimited continuations are sort of a generalization of that. What's different between those 2 things is that this continuation that we've captured is just an ordinary function. So you can call it multiple times, for example, and resume from the same place twice, which is, something that's useful if you're doing like backtracking search, but can be a little bit confusing. But a good intuition is to think of them as resumable exceptions. So just for completeness, let's sort of walk through the same example again, but using yield and delimit instead of prompt and control. And again, yield here is the red X. This bit here is the continuation. We are going to be passing the resumption in for k, and here I'm just yielding unit because that's not really what this example is about. But obviously in a real program, you could be yielding something more interesting. And so then again, we have these 2 bits of the continuation. We can split everything up, put them back together, and now we have exactly the same thing that we had before. So the only difference here is the syntactic location of that function.
somewhat naive question, but are delimited yield expressible in terms of prompt control?
Great question. So yes, I guess one of the both blessings and curses of delimited control is that they're these very powerful operations, and you can express them in any number of different ways, and they're all sort of mutually expressible in terms of each other. Now, one thing that I will get to a little bit later is that when we get to static typing of these operations, it becomes a little more complicated. I've carefully avoided not talking about static types in a Haskell talk. But it is indeed the case that these operations and indeed other forms of these operations are all mutually expressible. So that brings me to the question of why do we use prompt and control over something like delimit and yield? Why does this show up all the time? And prompt and control are actually very similar to shift and reset, which I think are probably a little bit more familiar to Haskell programmers, which are also almost identical to prompt and control. Very, very minor difference. And so I think there's a few reasons why historically we use those operations instead of operations like yield and delimit. So one is that these are sort of, they were introduced in a paper, they were being studied as just like a class of very powerful control operators, and given that context where you're just trying to distill out the essence of delimited continuations rather than build a useful thing, they are in some ways simpler. They sort of just do precisely what, they give you precisely the ability to capture a delimited portion of the continuation. I think maybe an even greater reason is that callcc existed. And callcc works this way because, again, it just left the continuation in place, and so prompt and control are similar to callcc. I don't think this is a great reason, but it is a reason. But then also, prompt and control, it turns out, are a little bit easier to statically type. So it is now finally time to talk about types, and I imagine some people in the audience were staring at me wondering when I would get to this point, maybe even a little annoyed that I'm not talking about types. And I do think that a lot of the time it's helpful to look at the types of things before getting into them. But what I've found when thinking about delimited continuations is that if you look at the types of these operations, they tell you almost nothing. They give you no intuition, and in fact can be misleading. And so I've been very careful to not talk about types until now, because I think if you really think about just the reduction, just the semantics, then the types suddenly make a lot more sense rather than the other way around. So it's worth starting out by saying that typing exceptions itself is not trivial. So we should expect that there's a little bit of challenge here. So if we just think about the type of throw, a lot of the time languages will just say, well, there's some exception type that we're throwing, and then they just return anything. Of course, in Haskell, we do this with type plus constraints, but there's some dynamic typing here in that, we have to essentially use the exception type class to essentially determine at runtime what the type of something is, and then run the appropriate catch handler based on what we've thrown. And that is a form of dynamic typing. So already, this is not fully statically typed. Returning, anything is not too challenging because that can just be universally quantified. And then the type of catch, it returns some B, so the body has type B, and the handler has type, it receives the exception, and then returns B. And at this point, this is where the dynamic typing shows up because we have to know which handler to actually call. Now, this doesn't provide any problems because in both cases, A and B here, these quantified type variables are just local to the throw and the catch, right? Throw just never returns, so we can just say, well, it just returns anything. And then we can say that, here the handler and the body just have to return the same type. But if we then start looking at, say, yield and delimit, we'll find that it's not quite so simple. So we can say that yield has, instead of an exception, we'll throw a delimiter tag, and you can imagine it working quite the same way. Delimit, again, just returns some type B, and these are now the obvious types for the different components. So this is obviously the captured continuation, where it accepts a value to plug in for yield, because yield returns an A. So if we look at the reduction rule, this corresponds to that. It has a hole. That hole corresponds to the point that we pulled the yield out of. And so therefore, yield returns is typed to return an A. So the context of the yield expects to receive an A, and therefore the continuation is a function that accepts an A. And similarly, then the B just works as it did for throw and catch, where this is just the type of, the delimiter. And because the continuation is in this particular case, because the continuation in this particular case corresponds to that E2, corresponds to that E2, then that's what the delimiter is expecting to receive, and therefore the result of that continuation is going to be B. Now, there's a problem with this, which is that now we have this A that's snuck into the type of handler. And that's a problem because it's universally quantified in the type of yield. So in a sense, this A is sort of out of scope. And we would need some additional mechanism to connect that A in yield with the A in handler. And in fact, one other problem with this is that if the yield is used in two different places, where one use of yield is used in a place that expects an integer and one is used in a place that expects a string, then that would mean that we have two different A's. And it's not entirely clear, maybe we could say, well, every yield for a given handler only has to be used in a place that expects the same exact type, but in general, that's sort of restricting the system a little bit, so maybe that's not a good design. So if we look at prompt and control, we have something that's sort of a similar problem, but kind of in reverse. So here, I'm just going to use B to be the return type of prompt, just to be consistent with previous examples. And now we have this familiar type for control that many of you may have remembered seeing at some point, which is very confusing. But again, if we look at the type, or if we look at the reduction rule, then it makes sense, because this bit corresponds to the captured continuation. It's that A to B function that we saw before. And it accepts an A. But now, because control is in the position of yield, the control operation itself returns that A. And the B corresponds to the type expected at the return of prompt, or the return of E2. Now, you'll notice that at this point, we sort of have the opposite problem that we had with yield and delimit, because now B is something that comes from the location of the prompt, but it also has to show up in control. So it seems like we can move the problem between these two things, but we can't really get rid of it. But as it turns out, it is easier to solve the problem with these operations, which is why I think we see them more often. So first of all, does all this make sense? I know that this is like the most confusing part of this talk, but hopefully, all right, all good. So,
One question too, one slide back.
Yes.
The delimited tag is just a way of associating the yield with the handler, right?
Yeah, well, so you can, so it's like the thrown exception.
Repeat that question.
Yeah. So the delimiter tag is just a way of associating the delimiter tag with the handler. That's
Yield with the handler.
Yield with the handler. So yes, you can think of it as it's the value that's thrown to the handler, like an exception is. But as with exceptions where we can sort of use that to pick a particular handler, you can imagine that also being the same. And this is maybe not a particularly great name. It's just a name I came up with. Yes?
But could you not then have it say the delimited tag with the type so you can connect it?
Indeed. Well, that's where we're about to go. It turns out that if you try to work through this process for yield and delimit, what you'll discover is you will invent algebraic effects. And this is not a talk about algebraic effects. So if you'd like to sort of see a worked presentation of that on operations that look like this, then there's a wealth of algebraic effects literature out there about it. And indeed, I actually think it's useful to think of algebraic effects as sort of a nice typed API to delimited continuations. And I think that actually the challenge of doing that is one of the reasons that they didn't see adoption for a long time, and now we have algebraic effects, and so people are interested in them. Yes?
Why is it that the F is thing is why can't that be part of the
Why is it that the F is... Why can't F be part of the E1? Like this F?
Yeah, so then just always
Well, why couldn't it just be part of the E1? Well, because it would be like in the case of having catch, there's the bit in E1 that continues, but then you also want to do something else when an exception gets raised.
catch makes sense, but the other three doesn't.
Yeah, you could have that in Haskell we have an operation called try, which just returns an either instead of having an explicit handler. And you could, encode this in the same way where instead of having the F be an argument to delimit, you could just make this return either the returned result, or either on the right the returned result, or on the left a tuple of the continuation. And that might also be challenging to type for other reasons, but you could you could certainly express it that way. And again, this is one of the reasons that I think delimited continuations have become so mystical, is that there's like a million different ways to encode them, and nobody does it quite the same way. All right. So going back to here, if we want to come up with static types for these operations, we can introduce tagged prompts, which is sort of like, with throw and catch, where you can introduce, or you can have different types of exceptions that say, like, I want to only catch, or I want to throw an exception that's only caught by a particular catch handler. We can introduce the same basic idea for prompt and control, but we're going to do it in a slightly different way, just to make it both a little bit simpler, a little more explicit, and to remove the dynamic typing, or at least to replace the dynamic typing with a sort of more explicit check. So we introduced this new operation, new prompt tag, and in Haskell this would be, IO prompt tag B, which is indeed what we have. But here in pseudo Haskell, we're just going to make it a function, a nullary function, takes a unit, and it just produces, it's like a unique. It can only be compared for identity, but it's indexed by this type B. So then when we have the prompt here, which now accepts a tag, and the control operation, which also accepts a tag, then now we still have this continuation, but this argument, or this type argument B, now connects all of these different types together. And so the prompt tag itself is just, it serves two functions. One, as an argument to prompt and control, those tags have to be the same in order for the control to abort to that prompt. But then additionally, it serves as a witness that connects the expected type from that prompt down to the type of the continuation in control. So it just sort of is a dynamic value that allows that type information to flow down to the location where we use control. Does that make sense? Yes?
Why do you have to make the tag first? Prompt, what is the lambda, the tag, and then it's magic?
That's a great question, and in fact, I gave this talk, or a slightly modified version of this talk at Lambda Days 5 days ago, and Simon asked me precisely that question. Yes, I can repeat the question. So why is new prompt tag a separate operation, rather than just making prompt accept a lambda that receives the prompt tag? So basically, prompt also generates a tag that allows you to abort to precisely that location. So I think you could do that, and certainly, actually, it was funny that Simon asked me that question because he's a co-author on a paper that presents a design that works exactly that way. But I think that this approach is actually kind of nice, both because it separates out the generation, this identity, synthesizing a new prompt tag, and then you can use that prompt tag and associate it with multiple, with multiple prompts. So in the same way that you might have multiple handlers that catch the same type of exception, you can have multiple prompts that sort of capture uses of control using the same tag. Another reason for this is that if you wanted to sort of really just prevent those prompt tags from just being returned and leaving the scope of the prompt, then you'd have to have some ST-like higher rank polymorphism in there, and that just makes the types more complicated. And there's really no reason to do that, right? It's just a pointer comparison, essentially. It just exists to have identity, and we can just have them be these distinct values. Now, it is true that maybe in practice that is a common pattern, and so a library could provide something like that. Yes.
Does it make sense for several prompts at the same time?
Well, you'll note that I haven't actually really described any of the applications of these operators in too much detail, but I think it does, because if you think about algebraic effect systems, which are sort of used to model the same sorts of things that we model with Monad transformers in Haskell, you might have multiple state effects, or you might have multiple error effects, and in that case, you want the sort of more local one to win. A good example is that if you're actually implementing exceptions using prompt tags, or using control and prompt, which you can do, then you might want to have two nested exception handlers, where one is sort of a local exception handler, one of them is a more global one, and in that case, it's useful to have them share the same prompt tag, because in that case, then, they can, just depending on whether the local one is present, then it will capture that use of control, and then if it's not there, then the outer one will. So, you don't have to do this, but it simplifies the system, I think, in a way that makes things a little bit easier to reason about as just, like a distillation of the system. All right, so we have now talked about continuations, delimited continuations, and first-class continuations. I'm not going to spend much more time talking about, here's all the fancy things you can do with first-class continuations, because again, I feel like Haskell programmers are actually probably most equipped to already know that there are nice, useful things you can do with these, like implementing, exception, state. You can use it to implement coroutines. You can use them to implement, like logic T-like things. But this raises the question of why would you want to do this with delimited continuations, given that we already have monad transformers to do it? And the answer is essentially just performance, but that raises the question of how do we actually implement these things? And that brings us to this last point, which are native first-class continuations. So it might seem like this is a complicated thing to implement because, again, we're taking a portion of the executing program, reifying it as a function, which, again, we've just been talking about in this syntactic way, but that sounds really complicated, and it seems really slow. One thing that we could do is we could use continuation passing style, which is, if you use some kind of CPS monad, then you can explicitly thread the continuation through the computation as a lambda, and then you can just at any point say, well, give it, hand me that lambda. And so there are monads that have implemented this in the past, and so technically, the work that I did recently did not bring delimited continuations to Haskell, because you could always have used delimited continuations. But this is fairly slow, or it can have significant overhead, and if you're interested, I gave a talk about that 3 years ago at ZuriHack, and you can watch that talk. So a nicer way to do it is to bake them into the runtime, because surprisingly, despite this being a super high-level idea, there's actually a really efficient implementation that's not very complicated of delimited continuations. So in order to understand what that looks like, we can take a look at just some hypothetical continuation here, and there's another way to look at it, which is like this. We can divide it into a sequence of nested continuations like we did before, but now they're sort of minimal in that you can't divide each of these anymore, right? They're sort of the smallest sliver of a continuation, and they're all nested inside of each other. And we can call these individual sort of continuation slices a continuation frame. So any continuation can be decomposed into a sequence of nested continuation frames. And what does this look like?
Stack.
A stack. This is a call stack. This is indeed, has a very direct correspondence with the actual call stack that, say, GHC or some other compiler uses to represent where you are in your program. And I mean, this is actually a good way of thinking about it intuitively, that the call stack keeps track of what's left to do in your program. So the call stack is the continuation, which is kind of cool. So if we imagine some kind of like abstract machine, and now we're gonna, for the first time in this talk about some actual operational details of some machine here, where the redx is this control operation, and the stack looks like this, then what actually happens? All we have to do is walk the stack to find the prompt. So we'll start with this frame, say that's not the prompt, look at this frame, that's not the prompt. Here we found the prompt, and so now these frames highlighted in red, all we have to do is copy them into the heap. So we have now literally taken these stack frames, copied them into the heap, we removed them from the stack, and then we also removed the prompt from the stack. And now we continue execution by replacing that control operation with G applied to some heap object, which I'll call cont here, which contains a pointer to those heap allocated stack frames. And that's it. That's all we have to do to implement continuation. Now, of course, the question is what happens when we apply that continuation, because now it's a function, right? So this is a special function. To the programmer, it just looks like an ordinary function, but to the runtime, it's a special function represented by this chunk of stack frames. And so then when we apply it, say to this string hello, then we just do the process in reverse. We just take these frames, we copy them back onto the stack, and then we continue execution from there. And that is the entire implementation of delimited continuations, which, as if you've been paying attention, is literally just memcopy. And memcopy, okay, so you might say, well, memcopy, it's linear time in the size of the stack frames that we're copying, which is true. But keep in mind that even though we're illustrating it like the code itself is contained inside the stacks, you might say, well, what if I have some really big program? Then this would be very expensive. But keep in mind that each frame is really only storing a pointer to that bit of code. It's not actually containing the code. So each one of those frames just corresponds to the nesting depth of the expression. So in reality, a lot of the time, this is just, a few words. And what that means is that, computers are really good at doing block copies of a few words. So in practice, this turns out to be remarkably cheap. Now, of course, there are pathological cases where maybe it's more expensive. And so, there are ways to optimize that. And if it turns out that people hit performance pathologies, we can maybe take a look at that. But remarkably, and this super high-level operation just corresponds to this very, very low-level operation, which I think is kind of neat, and is actually, I think, one of the best arguments for languages should have delimited continuations, because they're not that hard to implement, and they give you a lot of control over this very low-level operational detail. Yeah, pun not intended, actually. All right, so we have now covered continuations, delimited continuations, first-class continuations, native first-class delimited continuations, and that's really it. Now, of course, there's a few things that I want to mention, a few miscellaneous details that I've sort of glossed over a little bit. So you can optimize this further if there's particular assumptions you know about how the continuations will be used. So for example, in OCaml, they didn't just implement what I've described here. They implemented one-shot delimited continuations, which is to say, I guess they're not linear, they're affine, where you can only resume from that point 0 or 1 time, not multiple times. And the advantage of this is that you can optimize it so that you don't do as many copies, right? You're just sort of swapping a stack in and out of what you're currently running, but you don't have to be actually copying things around. And so they're using that to implement sort of user programmable thread schedulers, because that turns out to be, if you're just kind of yielding from a thread and then resuming it later, then you can represent that way. And, of course, this is something that if it turns out people want to do in Haskell, we could add operations to have sort of a special first-class continuation. Maybe we could even use linear types to help with that. So also, obviously, I have been talking about this sort of strict pseudo-Haskell, and Haskell is lazy. So in the real operations we have, they all live in I/O, or really, state hash, which is the implementation of I/O. And that allows us to have predictable ordering and a predictable continuation in a lazy language. What this does mean, though, is that you can't, for example, copy or capture the continuation across like a use of unsafe perform I/O. Because once you do that, you're going into lazy code, and then the order in which things are evaluated is not well defined, and so the continuation is not well defined. So we have some restrictions on how they're used in Haskell, but as long as you're working monadically, then you can do this, which corresponds, I think, intuitively to in the past, if you wanted to get continuations, you would use some monad. And so the interface hasn't really changed. And of course, in reality, it's not just memcopy. There are a few other minor details that we had to worry about in GHC, but they really were quite minor. And it's really remarkable how little, how small the patch was to implement this. And really the most complicated thing was really just getting, if you're capturing a continuation, and that means you're unwinding the stack, and you manipulated the asynchronous exception masking states, then we have to save and restore that, and that is a little bit more complex. Yes? Can we have a version that works in ST? So I think in strict ST, it should work fine. In lazy ST, it won't. I think, and I guess currently there's a way to convert safely between strict and lazy ST, and it's not an unsafe operation. So I think because of that, probably not in any safe way. But if you are just using strict ST, and in fact, the intent here is to use these to implement an algebraic effect system, which I have a library that does do that. It's not published yet. I need to finish it. Maybe I'll finish it today. But that provides a pure interface to these things, in that, if you are doing I/O operations, which you can do, then you represent that at the type level, and it's an impure computation, and then you have to run it in I/O. But if you're not, if you're just using state and reader and things like that, then you can discharge that entirely in pure code. So yes, it's kind of a long-winded way to say that yes, you could make this totally safe to use in pure code. Yes?
It's kind of hints at that maybe kind of a universal strict control structure. Can you express all of the control structure in it?
So can you express all of the control structures in terms of these? Well, so it is true actually that in an earlier version of this talk, I said, well, maybe we can define a control operator as a thing that manipulates the continuation. But I thought about that a little bit more, and then I thought, well, if then else is a control operator, and it doesn't manipulate the continuation. So I think maybe there are certainly a lot of control operators that can be expressed this way, but there are also control operators that can't. You could imagine a really strange and exotic operation that, say, if you have some reactive programming language, synchronous reactive programming language like SRL, where evaluation works in a different way, then you couldn't encode something like that using these. So it is very expressive. You can encode lots and lots of things into it. And certainly, I guess one answer to your question is that there is a very well-known correspondence between monads and delimited continuations, in that you can, anything that you can express using monads, you can also express in terms of delimited continuations and vice versa, with just local transformations between the two. So basically, if you can express it in a monad, then you can express it this way. So it really is just like for Haskell, it really is just an implementation improvement. Yes?
Can't it have these linear types to capture stuff, copies, or like applies twice?
Could we use linear types to...
Like what happens to linear types?
What happens to linear types? Well, that's a good question. So, I mean, the truth is, I can answer this with, I haven't thought about it and it doesn't matter, because there's no safe API to use these primitives exposed in base. So the idea is that you wrap it in a, in a safe library that does allow you to do these things. But that's sort of a cop-out, because, it doesn't really answer the question. I mean, linear types, they don't have, like from the perspective of the runtime, there's nothing special about them. They're just a type level thing. So currently we don't do anything special by like making assumptions, I believe. Is that right?
Yeah.
Yeah. We don't do anything special at the level of the runtime. So you could, because these are unsafe, you could implement something that doesn't respect linear types. Just don't do that. But it is interesting to think about, like, what would the implications be? Could you combine these with linear types? I think it would probably, you'd have to somehow restrict, you'd have to prevent somebody from resuming multiple times from the same place if you had something linear going on. And there would be ways to encode that in the type system. Yes?
You mentioned that one-shot continuations could be more efficient. There's also ways of including generalized continuations
in terms of one-shot continuations.
Yes. You sort of repeatedly generate new ones.
Right.
Do you think you would get back the same performance or worse? Like, does this generalize to a one-shot implementation?
Does this generalize to a one-shot continuation implementation? So, I mean, certainly, I think we could add one-shot continuations. Maybe I don't entirely understand. Like, are you saying if we implemented delimited continuation or multi-shot in terms of one-shot, would that be appreciably, better or worse? Well, so it would be strictly worse in the sense that then if you're truly using them as multi-shot continuations, in that each time you resume the continuation, you then have to capture it again, which means that you're copying the frames back onto the heap or back onto the stack and then back onto the heap. So you're just doing one additional copy in that cycle. One shot, this is the frustrating thing, is that if you really read, like, there's all these papers on here's cool tricks to implement callcc more efficiently, but then it turns out that the only thing that people actually use callcc to implement are delimited continuations in practice. So and if you're just doing delimited continuations, then it's much harder to have some general purpose optimization, something that doesn't make something worse. There are ways to, for example, if you know that you're going to capture the continuation for sure, you can maybe say, at the prompt, allocate a new stack, and then, connect it to the old one. And then when you do the control, you just disconnect the stacks, so you don't have to do a copy. But the problem is that then if you don't capture the continuation, you've allocated a whole new stack that you then just throw away, so it's actually worse. So, there's all these different use cases you can specialize for, but the one that we have in GHC, I just decided to do like the simplest thing, and then we can see how people use it. And they're still pretty fast. Yeah. All right, any other questions? Yes.
So with this stuff, you are building these stacks of the ambient control flow. As it makes it a little queasy. Doing a thing that's trying to value now. Another thing you could just have is you just build stacks from scratch. Or like I don't want this big,
Have you considered ever trying to make sort of first-class stack building separate from control operators?
So the question, I think, is have you ever, the way that this works is kind of this magical reification of the control stack. Could you have some API that just allows you to build up those stacks in some other way, and then without doing this particular process, So, some API for building first-class stacks that isn't, that's explicit, where you sort of say add a frame here, add a frame here. And I think my answer to that question is that is what function application is. In that when you apply a function, or when you, have some expression, some nested expression, and you have a function application and then some argument, some sub-expression, then that is pushing a frame on the stack that when it returns will, the API for manipulating the call stack is what, is just writing code. Could you have, would there be some advantage to having some way to explicitly add frames to it? I don't think so. I don't think it would buy you very much. Maybe I'm not envisioning what you are describing, but I think that basically, you could implement an interpreter that, you build up a stack of expressions and then you interpret it, and that would translate it into a call stack effectively. But again, I don't think you would gain very much by doing that. But maybe I'm just insufficiently imaginative.
Thanks.
Yes?
Is there some violation of referential transparency possible? And I'm wondering if there's some kind of violation of referential transparency that can occur because the value of an expression now depends on the context.
Yes. So, are continuations impure? Yes. These operations do depend on the context, and that's why, we can only use them monadically. You have to be in some, monadic context that allows you to do that. Now, the sort of violation is very well defined. It's just that, rule, that evaluation rule. And in practice, because you don't care that much about the actual structure of the computation, so I guess here's the thing. If your computation, all it does is capture the continuation, then the order of evaluation, relatively speaking, between, two statements in a monad doesn't matter because, aside from the data dependencies inherent in your program. So if you just think about, okay, I have the rest of the program that just produces some value, then it's only depending on the context in the sense that, whatever the rest of the program happens to be is what you're capturing. But otherwise there's no weakening of those properties. But it is true, of course, that, that has to be well defined in order for the meaning of these to be well defined. So the context does matter.
Okay, thank you.
Over there. Yes? Could you introduce accidental space leaks when you save the continuation? So, saving the continuation will retain a reference to anything that is, actually needed by the remainder of that computation. There is actually, I guess, an interesting parallel between that and, say, when you have a thunk that's being evaluated and an asynchronous exception is delivered, then GHC will suspend the evaluation of that thunk in much the same way, actually. It will copy the stack that was being used to evaluate that thunk onto the heap. And then when it is resumed or some other thread forces it, then it'll continue from there. So all of that work that was being used by that thunk will be saved. And if that thunk is never forced, then it will all be retained. And the same thing is true for a continuation. But all of that is stored by the continuation itself. So if you're retaining the continuation for too long, then sure, you could leak all of the resources needed by that continuation, but it's not, there's nothing different between that and storing a reference to a closure, a function closure, right? The function closure also has to keep references to all the things it needs. So it works in essentially the same way. There's no difference.
Thank you. So earlier we had a question whether we can express all control operators in terms of continuations. And we know that continuations have an isomorphism to monadic, to monads. And I have a hard time imagining that there's a control operator that can't be expressed as a at least really stupid monad, right?
Okay. If you have a Turing-complete programming language, you can express everything. The question is, there's this notion of like Falaisian expressiveness, which is, can you perform some local transformation to encode something? And there are other languages with like weirder evaluation semantics where you can't directly encode that monadically. I think that's kind of outside the scope of what I'd like to talk about right now, but one example of that I gave is synchronous reactive programming languages. So things like that, they have sort of weirder notions of evaluation order. And so it's not a well-defined question, like what constitutes a control operation, what doesn't. Depending on how you define it, you could say, oh, sure, these are universal, but then I think it would be sort of tautological, so I'm not sure that it's a super interesting answer to the question.
Yeah. Mm-hmm.
So despite how simple it is to actually implement this thing, GC didn't get delimited continuations like you described until 9.6. In your opinion, what took so long?
What took so long? Well, I think, honestly, so as nice as these are for implementing certain things, they're also not like, we can do them in Haskell monadically, right? Using monad transformers or by implementing a delimited continuation monad in GHC with CPS. So I think given that people were not, have not been wildly using the delimited continuation monads that already exist, this suggests that maybe it's not, a super important, super critical feature. And we were able to get a lot of the same benefits in Haskell, whereas other languages might not because they don't, use monads in this way. So I think maybe in the case of GHC, people didn't see the need for it, and also there's just not that much knowledge within the GHC community about continuations, how to implement them, what they are, and so I think it just kind of took somebody saying, well, let's do it, and then it wasn't particularly controversial, but nobody had just said, well, let's do it. So not any particularly deep reason, I think.
Could you say something about your plans for algebraic effects and how it depends on this?
Something about my plans as to algebraic effects. So I have a library on GitHub, it's called EFF, that is not quite done, it's not released on Hackett. It's existed for a number of years. That was the original motivation for doing this. I would like to finish it. I think that it provides a nicer semantics for certain things than other effect systems that already exist, but I'm also very reluctant to add to the ecosystem fragmentation problem that sort of is already there, because we have, a million effect systems already in Haskell, so I'm very cautious about that. But I would like to do that, and I do think that, libraries can use these primitives and get nicer performance for those things, and so maybe at this point, I need to go back and take a look at some of the more recent effect systems that have been developed, and maybe we can at PR a more efficient implementation and keep the API. I'll see, I'm not sure.
Let's do one more question.
Did I understand correctly that you previously said that there's no safe way to use the native primitives?
So there is no safe API in base currently exposed.
Okay.
We could...
Then what I don't understand is we already have the delimited continuation monad.
Yes.
And that one is safe to use.
Yes.
Isn't it the same semantic?
So the answer, that's a very good question. So we could expose an API in base if we wanted to, or somewhere else that provided that same API using these primitives, and it would be totally safe. However, what I found when I was implementing the algebraic effects library is that I wanted to do things, and I wanted more control over that anyway, because basically any typed API or any typed restriction you give does to some extent restrict how you can use them. And it's not clear to me, or at least it wasn't clear to me, that given that we don't have a ton of users of that API already, it's not clear to me that that would be all that useful. And it would be a maintenance burden to then say, okay, because base is very strong backwards compatibility guarantees. It's kind of a headache to change things, and it's not clear to me that it would be worth it. Because again, the compelling use case here was for implementing algebraic effect systems. That would not be an algebraic effect system. I probably wouldn't use that to implement an algebraic effect system. So if it turns out that people are really excited to use the delimited continuation monad API, then absolutely we can package it up that way. It's just not something that we've done so far. And I guess one other thing I'll say is that the unsafety here is mostly just that it runs in like I/O. Why don't we expose it in I/O? because of the fact that if you have some existing I/O code, it's not going to handle reentrancy. So if you have some code that like opens a file using with file or whatever, and it uses brackets, and so it expects a resource to be reliably deallocated when control leaves that, and then you capture the continuation and suspend the computation, then who knows whether or not that code wants the file to be closed or it wants it to stay open until continuation resumes. So it's easier to just say, well, I/O code does not get to use this, and you have to introduce some other thing that is for new code that does take on the obligations of worrying about those things. But otherwise, there's not any deep unsafety there. It's just that sort of logical unsafety. It's not going to compromise aspects of the runtime. All right, I'll wrap this up because we're over time now by about 20 minutes. So I was just going to say we also lack continuation benchmarks. So as people start using this, it will be really great to hopefully accumulate some benchmarks and test cases so that we can actually see, well, are these performing as well as we'd like? And I guess one last final point is that reduction semantics are really wonderful. This way of reasoning about programs as just a sequence of reductions, because we were able to talk about all of these things without, except at the very end, talking about like a machine with a heap and a stack. We could talk about very, very complex things just in terms of the source code of a program, which means that in those sort of sequences of reduction, you could take any intermediate step, and that's a program, and you could resume from there. And so this is, it's a nice way of reasoning about lots of things, including continuations, and I think that people don't talk about it enough. So I wanted to mention it, and you can, look up reduction semantics or small step operational semantics if you want to learn more. This is not that important. I'm going to skip it. So recap is just continuations show up when we talk about evaluation. There's operations like catch that delimit it. First-class continuations let us reify it. And this has a remarkably efficient implementation, which is why it's really great that we have delimited continuations now. And that's it. Thank you.